Welcome to section 6.6. So this is the last section of chapter 6 that we'll be discussing. We won't be covering the harmonic motion section in 6.7. In this section we're looking at the graphs of the secant and the cosecant functions. So we know that the secant function is the reciprocal function for cosine, and cosecant is the reciprocal function for the sine function. Alright, so we know what the graphs of those look like. So like if you go to your graphing calculator, go to y equals, and let's say I wanted to do cosine x, a graph. Alright, we know that this is our cosine function. We know the period is 2 pi. The amplitude is 1. Let's use a calculator to help us see what the reciprocal function for cosine would be. So reciprocal function for cosine, we want the secant function. So let's go back to y equals. Alright, now how are we going to type in secant of x into our calculator? There's no secant button. So you have to do 1 divided by the cosine to get your reciprocal. There's your x, close the parentheses, and graph. So this is what the reciprocal of the cosine function would look like. So remember, cosine was just kind of oscillating between 1 and -1 on the y-axis like this. Cosine is going to be above the original graph or below the original graph. So it's never going to overlap where we had cosine running through the middle. Okay, so your reciprocal functions are going to be above and below the original functions. Now, as far as how to graph these things, this section, to me, in my opinion, is not very difficult, because the rules here, and I'm going to let you read through the guidelines here on your own. I'm not going to read all of this. But long story short, what you're going to be doing with these, the secant and the cosecant functions, is, say you're asked to graph a secant function. Well, you'll start by graphing its reciprocal, the cosine function. And if we go back to our cosine function, any place that my cosine function touches the x-axis, so any of these x-intercepts, when the cosine function is equal to 0, if you think about this, it'll make sense. When cosine equals 0, its reciprocal would be undefined, because 0 over a number, you flip it and you get 0 in the denominator. So anytime that your cosine function is 0, your reciprocal function, the secant function, will be undefined. So that means that any place that you've got an x-intercept on your original graph of cosine will be a place to put in a vertical asymptote for undefined values for the secant function. Okay, so we'll start by looking at the graph of the original base function, or the original guide function is what we'll call it. Alright, and then we'll take the vertical asymptotes based on those x-intercepts, and then we just go back and look at what what did the secant function look like again? 1 over cosine x. So we have what looks like these U-shaped branches up here and down here, and they're always going to be in between those vertical asymptotes that you drew based on the x-intercepts from the original function. Okay, so this is what your secant function would look like, and the asymptotes that you don't see but they are there are coming from the x-intercepts from the cosine function. All right. So let's take a look at how this is going to work. Again, I encourage you to read through the steps that I've put here for you, but we're going to jump right into our examples. So in example 1, we want to graph y equal 3 times secant of 2x. Alright, well, let's start by let's graph y equals 3 times cosine of 2x, because that would be the reciprocal function. Okay. Now, what's happening with the cosine function in this example? I see, look at this, I notice I have an amplitude of 3. So we see that our amplitude is 3, and our period for the sine and cosine functions is going to be 2 pi over b. Okay, so my period is 2 pi over b, or 2 pi over 2. So the period for this one is pi. Okay, so we know that the cosine function would start at the y-axis, and it would go it would complete its first period. And let's see, we'll put that at pi here. So we're going to have this shape. Let's see, it's going to touch at 3 up here. It's going to come down to -3 because the amplitude is 3. And let me change this. So the complete period will be pi. So that means we've got pi over 2 in the middle. This will be pi over 4. This will be 3 pi over 4. And we can draw our function. So our cosine function is going to go through like this. We have an x-intercept at pi over 4. And let's see. And then it's going to come down to here. So it'll be at pi over 2 comma -3. And then we have an x-intercept at 3 pi over 4. And it'll come back up to the order pair pi comma 3. Okay, so this is this is 3 cosine of 2x. Now, to get my inverse, let's be careful. Be really careful. I just made a slip up, and this is something that is easy for you to get mixed up in as well. A reciprocal and an inverse are not the same thing. So we're going to be talking about the reciprocal function, of course, meaning the secant function. Okay, we know that's not the same thing as an inverse function. So to get my reciprocal function, secant, I'm going to first change color because it's going to all run together if I don't do that. So let me real quickly find a different color pen. So we'll first put in our vertical asymptotes, and they're going to come from the x-intercepts. So we'll put in a vertical asymptote at pi over 4, and we'll put another vertical asymptote in at 3 pi over 4. Okay. Then we're going to sketch in those U shapes that we saw from our calculator from the secant function. Now, how do we know which U shapes go in which? Let me extend this out a little bit more first. So if I take it back this way, so we can get a better picture. So negative pi over 4, negative pi over 2, negative 3 pi over 4, and then I could come back a little further and have negative pi. So my cosine function is going to do this. Come down here, and then go back up like this, and go back up. And I could put in 2 more vertical asymptotes at the x-intercepts. Okay, and now to put in all the U shapes for the secant function. Just be careful that your secant function and cosine function should never overlap. So because the amplitude is 3, if you want to put in a dotted line here, you can, just to make sure that your secant function does not come below this line. And then down here, the secant function cannot cross, it cannot dip into the amplitude of the original cosine function. So make sure that your U shapes have to be strictly below and strictly above your cosine function. So now how do we know where the U shapes need to go? Well, if the cosine function is taking on positive values like it is right here, then the U shape needs to go up here above it. And I apologize, it's kind of running together with my original problem. But my U shape would be up here. Okay, over here where the cosine values are negative, then the U shape is going to be down here. And then over here, it's going to be back up again. And just be careful that it doesn't dip into the original cosine. Back here, the cosine function is taking on negative values. So secant is going to be under the function this time. Back here, where it dips back up, it's going to look like this. Okay, so it did kind of run together, but that is how we'll graph our secant function. You just graph the cosine first and put in your vertical asymptotes at each of the original x-intercepts. Put in your u-shapes, and if the original function has positive values, then you put a u over the function. If it has negative values, you put the u under the function. And that's it. That's your secant. Let's look at example 2. Here we want to graph y equal cosecant of x minus pi over 2. Alright, so we need to start by graphing y equals, alright, the reciprocal function of cosecant is sine. So we want sine of x minus pi over 2. Okay, so we'll graph sine of x minus pi over 2 first. Okay, now we know that our sine function has this shape, and its original period would be 2 pi. In this function, b is 1, so we still have period 2 pi. But notice we also have this phase shift of pi over 2 units. So the original sine function has to be shifted over pi over 2 units to the right. But that's the only thing that has to happen with it. So if we move it all, let's see, if we had, I'm going to put in the marks like I would if I had my original sine function here. Like this. So like if I had the original sine, if I had just regular sine of x, I would go up to 2 pi. So I would divide this up as that would be pi over 2, 3 pi over 2, and 2 pi. Okay, but we're going to shift it pi over 2 units to the right, so now it's going to start here, and it's going to go one more pi over 2. So 2 pi plus pi over 2 would be 5 pi over 2. The amplitude for this one is 1. And I'm going to extend all of these over to the other side as well. So I got negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi, negative 5 pi over 2. So just drawing one period of this sine of x minus pi over 2 will look like this. Okay, so that's what that sine function looks like. To get our cosecant function, we'll put in the vertical asymptotes at the x-intercepts, the same as in the previous one. So let me change my colors. So we'll put in our vertical asymptotes at each of the x-intercepts. Okay. And amplitude was 1, so when you start drawing your U-shapes above and below, be careful that it gets really close to 1, but it can never touch it or cross it. So in this one, our sine is taking on positive values, so our U-shape would be above the graph, like this. Over here is sine is taking on negative values, so we're going to be below the graph, like this. Okay, and we can extend this out to another period. So we could come back and go here, 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 and here. So if your original sine function is this, then your cosecant function will look like this. It'll be, you could put in another vertical asymptote here and one here. And you can draw your U shapes. This one will go below, and then you'll put one up here where the function takes on positive values. Okay. Okay, and if you wanted to go again, you could, if you wanted to continue, you could draw another one down here as well. But that is what cosecant of x minus pi over 2 looks like. Okay, so just start with your sine function, and then just putting your u's above and below. That's it. Okay, example 3. Okay, this is the example that I had to fix the graph for. My original sketch was not accurate. So when you do example 3, please use the file that was posted separately in Blackboard for example 3. I had originally drawn this like it had a vertical shift, but it's not supposed to have one. Okay, so when I approach this one, they've given me a graph, and I have to give the equation for the graph. So of course this is still going to be either secant or cosecant. So you don't have to worry about tangent and all that stuff right now. But so let's start by drawing the reciprocal function for this. So we don't know yet if it's a secant or a cosecant, but if I draw the reciprocal function for this, it should be going. It should start here, and then it should come down like this. So it would touch here because there's an asymptote, so I know it's going to touch here. And it needs to go up to where the other one comes to, and then it needs to come down like this. Okay, and then on the other side, it's going to go from here to the x-intercept, and it's going to come down and meet the reciprocal function down here. So this more like that. So what does it look like we're drawing? What function does that look like? If you just, and you're probably just, you might want to just look at it from here over like this. So what function does that look like? Oh, that looks like part of the cosine function, because the cosine function would touch the y-axis at 1. The original cosine function would. So it looks like we're definitely going with the cosine function. Now, do we have any type of shifting? Are there any changes with the period? I don't see any shifting, and I also do not see any vertical stretching because this is occurring at 1. So if we're so when x is equal to 0, cosine of 0 is 1, so that's correct. And when x is equal to pi, cosine of pi is 0, so that's looking good. However, what about the period for this? You notice it goes up to 2 pi here, but from starting back here, this is only half of a period, because it would need to go up again to complete it. So that's telling me that my period is actually 4 pi. So we got the cosine function, and we have period 4 pi. So our period we've determined is 4 pi. And we also know that with the cosine and the sine functions, it's also true that the period is equal to 2 pi over b. So if we set these equal to each other, we can solve it for b. So I've got 4 pi equals 2 pi over b. I can cross multiply. That'll give me 4 pi b equals 2 pi. Oops. Dividing both sides of this by 4 pi is going to give us b equal to 1/2. So we got b equals 1/2. So since we have our cosine function in purple and we've determined b is 1/2, there's no translations vertically, or no phase shifts to deal with, no vertical stretching. So all we have, so the purple graph is y equals 1/2. I'm sorry, y equals cosine of 1/2 x. Okay, our red graph is going to be y equal the reciprocal of cosine, so secant of 1/2 x. That's our answer. Y equals 1/2 secant x. I'm sorry, y equals secant of 1/2 x is what I'm trying to say. And that's the graph in red. So in example 3b, looking at this one, without even deciding if it's a sine or a cosine yet, it looks like it's been shifted down 1 unit. So, because you've got this peak here occurring at y equal -2, and you've got a valley here actually sitting on the x-axis. So that's telling us that the original sine or cosine graph has been shifted down 1 unit. So if this is my 1 here, then the point that it was originally at the origin, which would make sense, because if you try to draw this in, you would have it coming through here. So that indicates that it had a point originally at the origin before it was shifted. Now, if it had a point originally at the origin before it was shifted, then which function does that look like it's going to be? Let's fill in the rest of it first. So you can go like this, and then back here to there. Okay, so if we can, we could also extend it out one more. So let's say if it was going like this, if it continued to go like this. So if we just look at it from the y-axis, we would recognize that looks like the sine function. There is possibly more than one correct answer for these problems, just like we had in the previous section. But I'm seeing a sine function that has been shifted down 1 unit here. All right, so if that's the case, looks like we'd be working with cosecant. And so y equal cosecant of x, and it's been shifted down 1 unit, so it would become y equals -1 plus cosecant x. Okay, is there anything else going on with this thing? Do we have any kind of phase shifts? Oh, what about our period? The period for sine is 2 pi, and it would start here and it would go, that's only half a period, so if it goes continuing on, you should get a period of 2 pi there. So the period's the same, so we don't have to worry about changing the period. So it should just be, it looks like it's just going to be -1 plus cosecant times x. So it was just the reciprocal function for sine that had been shifted down 1 unit. Okay, it's -1 plus cosecant x. I hope you can see that okay, because my pen's about to run out of ink. Alright, but that is example 3b. Alright, the last little piece of information in this section is about addition of ordinates. This is a little bit of history of how graphing was done. I'm just going to read through this. It's not anything difficult. It's very straightforward. So we're just going to it's just a little bit of an introduction to something. So it states that a function formed by combining 2 other functions, such as y sub 3 equal y sub 1 plus y sub 2, has historically been graphed using a method known as addition of ordinates. The x value is called the, I'm not sure how to pronounce this, abscissa or abscissa. The y value is called the ordinate. Now in example 4, they ask us to use the function y sub 1 equal cosine of x and y sub 2 equal sine of x to illustrate addition of ordinates for y sub 3 equal cosine x plus sine x with the value pi over 5 for x. All you're doing is plugging this in. That's it. So you're going to say y sub 3 equals cosine of pi over 5 plus sine of pi over 5. And to make it even easier, they're using decimals. So you don't even have to look at the unit circle. You can actually type this into the calculator. Okay, so we are working in radians, so make sure your calculator is set to radians first. Go to mode. Mine needs to be changed. Alright, so I've got it in radians now. So I'm going to type cosine of pi over 5, close parentheses, plus sine pi over 5, close parentheses. And I'm getting 1.3968. And I believe that's correct. Yes, that's it. So we get y sub 3 equals 1.3968. We were not told how far to round this, so we'll just leave it right here, 1.3968, and we're good. So nothing to this. Don't worry about this stuff. This is all. If you're asked a question like this, all you're going to do is plug in the numbers. And that is that's section 6.6, and that completes chapter 6 for us. So we've got 2 more sections for module 2, 7.1 and 7.2. All right, thank you guys.